Hello YouTube. The last time I looked at RS485 with this little RS485 transceiver expansion board. This time I want to look at a higher layer protocol, a very simple, probably the simplest higher layer protocol that is usually transmitted over RS485, but because RS485 is just comes out as serial, I'm going to just use it directly over RS232 coming out of these cinnamonBuns. Now this is a Mark IV cinnamonBun with USB on it, and this is an old Mark III that I have kicking about that I'm just using for this test. And the protocol I'm going to look at is MODBUS, which is still used. It's quite an old protocol, but it's still used in it's used in industrial applications, so it's dating back to 1979. And this is actually, if I go to the home page of modbus.org, I'm looking at the technical resources and then MODBUS specifications. Now you've got to accept that the terms and conditions, but then they have a layer 7 specification, and this document down here is the layer 1 and 2 specification. Those layers refer to in the late 1970s, I think. Yeah, it was about then that the standards, international standards body, the OSI, tried to take what they'd learned from various computer protocols that had been invented since the dawn of computer programming, and tried to create, like, they'd looked at loads of implementations of protocols. People had used various different protocols for communicating, and OSI looked at the implementations, the architectures, what was being done, and tried to pull out a standard out of those to see what was the right way to do these things, having looked at implementations which are probably good, some of them bad, and tried to pull out the things that should be done. And they came out with a document that represented a protocol by 7 layers of a protocol. Now we've talked about RS232 and RS485, which would both be physical layer protocols. They define the communications medium, which is, in the case of RS232, is just a copper line. In the case of RS485, it's a twisted pair. But it also defines the electrical signals. So in the case of RS485, it's a differential signal between the two lines. So you've got one line is positive to the other, or vice versa, and that transmits a 0 and a 1. That's a physical layer protocol. RS485, a high voltage is the idle state, and that's also counterintuitively a logic level 0. And then when it falls down to a 0 volt on the line, that's a logic 1. And that's just the physical layer, the difference between two protocol implementations on a physical layer. So the MODBUS protocol probably predates OSI, and probably the publication of that standard, or at least if not the publication, then when that standard became to be respected and adhered to and used. So even though MODBUS predates the OSI model, they still talk about this being a layer 7 protocol document. And that's because all protocols after this OSI 7 layer idea became widespread. Even protocols that predated the OSI model kind of squeezed round pegs into square holes and tried to conform to that standard and say, well, this is where we sit on that hierarchy of protocols. Now lots of protocols like the Internet Protocol Suite TCP/IP wouldn't strictly adhere to the OSI 7-layer models, but we do talk about the IP protocol being at the network layer. And some people would say it actually straddles both the network layer, layer 3 and layer 4, the IP protocol. I'm not going to get into that here. We're just going to concentrate on this simple protocol. So this simple protocol is used in industrial automation, and assuming that you've accepted the license agreement for looking at this file, I just want to look at one element of this specification, the layer 7 specification, which is a message to read the coils. So that would be specifically for reading a relay. So this document is 50 pages long. I mean, it's very small for a protocol, and it's probably one of the smallest protocols you'll ever read, but it's a very simple protocol, and this is a simple message to read the status of a coil, which is a relay. So is it on or off? So if you had a light switch or a light controlled by a relay, is the light on or off? And the MODBUS standard it's described in this document as a client-server architecture. I don't think it is strictly a client-server, because that's for a different type of thing. This is more of a master-slave area where there's one master on the line, and it's sending out requests. So in this case, it can send out function codes, one of which is, I want to read the coil status, and I expect a response of 1 if something's on. So we send out 1 byte for the function code, and then 2 bytes. This is the master sending out a request. This is the function code, 1, read coils, 2 bytes of a starting address for the coil we want to read the status of, and then the number of coils we want to read. So if there were 8 coils, 8 relays controlling 8 lights, I want to read back all 8. The status of all 8 coils in one response. And then the slave responds. Now this is at layer 7, so layer 7 does not mention layer 2. So the layer 2 is our data link layer, and it's sending messages from specific nodes to another node. So that the actual protocol at a lower level has a destination address. So this is the application layer frame, which is then going to go down to layer 2, and the target address is going to be prepended to it and sent over the serial channel. And then the slave receives that, and we expect it to respond with the function code, which it just received, 1, read coils, and then the number of bytes that it's sending back to us, and then the actual bytes. So the libesoup project, the code's up on GitHub, contains example mains, 2 of which are MODBUS master and MODBUS slave. But also in that examples projects directory, there's a MODBUS capital M, 2 projects, master and slave. So I'm going to put the master is on this USB cinnamonBun Mark IV, and the slave is programmed into this cinnamonBun Mark III. So we'll connect that to the slave, and if we just look at the code for the slave. All the slave does is, if I go to the main, it sets up the GPIO for our serial port. Now this is assuming that we are running our 485, an RS485 transceiver. We're not, but it doesn't matter. The pins are connected, so we've connected the transmit of the master to the receiver, the slave, and the transmit of the slave to the receiver, the master. So, I mean, it's going to make no difference to the actual code. If we had the transceivers on, two transceivers and connected via RS485, they'd still receive the same messages, the same serial from the UART. So, as previously we set up a UART data structure to reserve a UART channel. In this case, we set up a MODBUS data structure, and we want this MODBUS to be at address 1. So this device is connecting on the communication channel on address 1. Now, addresses are valid from 0, but 0 is special, up to 247, I think. You'd have to read layer 2 protocol, but from memory it's 247. MODBUS address 0 is a broadcast address which the master will send a message to MODBUS address 0. All slaves are meant to process that message, but nobody is meant to respond. So it's a special case. So this slave, we're going to set up a slave. I should look at the sorry, where have I gone to? I want to get our configuration file. And in our configuration file, we're enabling the MODBUS with a switch, and we're selecting a slave. And we're saying that we want 2 channels. We're actually only using 1 channel in this, but I just set it to 2. Can't even remember why, but there's 2 channels. If we're sure we only needed 1 channel, then we just set that to 1. But we enable MODBUS, and we've selected slave here, but we could select both master and slave. And those 4 should only really be necessary for a master. So hopefully that. Yeah. So we've got the number of slaves and the buffer size. And MODBUS strictly says that the buffer size, that you can only receive a message which is 256 bytes long. That's written into the standard. So that saves us having to think of a number. That's the way it is. So our slave fills out the structure. It says we want to be, because we're using address 1, that implies that we're a slave. So we want to be a slave, and we're implementing the slave side of the protocol. And then this is our handler function, our callback function for processing messages. And all this callback is doing is processing read coils messages. So that's our read coils, is the only function code we're going to respond to. If we receive any other function code, we're going to execute this default and send an error message back to the master. So anytime this slave receives any other function code, it's going to respond with an error. Specifically, a function code exception. So the master knows, well, that slave doesn't actually implement that part of the protocol. So for example, if this node, we're implementing the read coil status. If our node didn't have any coils, then there's no point in trying to read the status of coils which don't exist. So if the master sent a read coil status message, we just respond to say, no, that's an error, we don't implement that. So we only process the read coil status. And the actual command that we're receiving, the function code we're receiving, which is this 01 read coils, is the first byte, of the request we receive. So we're switching on that first byte, and then when we process the message, because we've now decided that it's a read coils, we're actually processing, we're skipping that first byte and reducing the length by 1. So the remainder of the message, which contains the starting address and our quantity of coils, so it should be 4 bytes, we're sending that on to our process function. So all this test slave is doing, it's printing out the message that we've received, which should be 4 bytes because we've stripped off everything else, and putting together the coil address and the number of coils. And we're only going to respond to coil address 0. If somebody sends us if the master sends us a different address, we're going to respond with an address exception. So whilst we do process the function code read coils, that's a bad address. So assuming that we receive a read coil, we'll just send back, we're going to pretend we have 1 coil with 1 byte. So the lowest bit is set. In this case, that coil is on. And we're going to send that response back to the master. And that read coils response is in our header file. The 2 functions that respond with an error, and both of these functions, API functions, are only defined for a slave, because only a slave can respond to a request. The master sends requests, the slave responds to those requests. So that's our read coils response. This is the channel. We want to send this buffer of data. We're only going to send, in this very stripped down test slave, we're only going to send 1 coil status. We've only got 1 coil. So basically all our main does is fill out this data structure. That's the function that we want to be called when we receive a message for this address. The other callback is for if there's a broadcast message to address 0, then this is the function handler that we want to, the callback function we want to handle those messages, so that the API will send those back. And so we reserve that MODBUS channel and we just loop around doing nothing. So the slave just enters the main loop and does nothing. So if I set, now this is, we'll be looking at the serial logging. So 19K2, sorry. So if I turn on our slave, it's entered the main loop. All it's done is reserved a MODBUS channel, and because it's a slave, all it does is wait for messages specifically to its address. So it's initialized that MODBUS channel on address 1, and these are the callback functions that it wants to process, either a message to its address, MODBUS process, or to the broadcast address. And that's all our slave is going to do. It's just going to sit there waiting. If I close that project and open up the master project, the other side of the protocol, again it basically defines the MODBUS and slave, or sorry, master. So it wants to implement the master. So again, I've got to set the number of channels to 2. I can't remember why. And again, the buffer size is 256. I should actually remove that because it's not up for question. That's hard coded into the specification. So I must actually get rid of that as an option. as a switch. I suppose there is an advantage to keeping it there if you knew that you were only ever, even though the MODBUS standard says it can transmit 256 bytes of a message, if you knew that your implementation or your application, if you've only got one coil, in the case of our slave, we only know we're going to be sending one coil, 1 byte. Now that would include, there's a number of bytes around that, but the maximum message size could be 5 bytes. So you could probably strip that down, and yeah, maybe there's a good reason for having that defined there. The response timeout is if a master sends a slave a request, if it doesn't receive a response in a timely fashion, then it assumes it's not getting a response and times out. The other one is a turnaround timeout. It's detailed in the specification, but if the master sends a frame to the broadcast address of 0, then it has to wait and give all the slaves a time to process that message. So it's usually smaller than the response timeout, but it gives the turnaround timeout is give all the slaves time to process a broadcast message, and that's all that's been added into the libesoup configuration. So our master then initializes the GPO as usual and sets up the structure again, our MODBUS structure. This is our MODBUS app data. I should have actually named it better for this, but it's our application data for the MODBUS channel. And underneath the hood of most protocols there is a state machine, and our application data for the master can contain an idle state callback. So that's useful for, in the MODBUS protocol, the master can only ever transmit when the MODBUS channel is in an idle state. So the MODBUS channel will be in an idle state, and then when the master asks it to transmit something, then it goes into the transmitting state, and then it'll go into the waiting for a response state, and then when it receives a response, it will process that response and it will go back to the idle state. But it can only transmit a request in the idle state. So when it sends one message, it has to wait for a response. It either receives a response in that state or it times out and goes back to the idle state, but it can only ever transmit in the idle state. So that callback is just useful so that the master can check that it's in a state where it can actually transmit a message. Because if you try and transmit a message and the MODBUS channel is in a different state, it will just return an error to say it's busy. And in the slave we had an address of 1. As I said, address 1 to 247 is valid. Address 0 is a broadcast address, which is actually invalid. So this is our way of signaling to the API, the libesoup code, that this is a master. So this is the master node, it's address 0. And we've got no callbacks except the serial port. We set up the UART data for the serial port that we want to open, the channel we want to open. And then we reserve that. In the same way as we did for the slave, the master just reserves that a MODBUS channel. Now, because this is the master, we were doing the usual: set up a timer and call our expiry function every 10 seconds. And that's all the code does. It just does tasks then waiting for an expiry of this timer, and every time there's an expiry it's going to call read coils. So this is the message that the request it's going to send. So it's going to send the function code of 1 read coils, and then 2 bytes for an address and 2 bytes for the number of coils. Now our slave is going to accept messages for address 0. So our call is going to be on our application the channel. Destination slave address 1, the coil address of 0, and then the number of coils, which is a 16-bit value, but it's just going to be 001. And that is all defined in our header. So this is that API function, read coils request. So we want to send the master to send a read coils request, and because a master is the only one allowed to send a request, this is underneath a switch. So that's all the code does, is every 10 seconds sends a request to Modbus address 1 node, what's the status of your coils. And this is a callback function that we want called when we receive a response. So we can fire and forget. Like our main just wanders around this loop, continually checking. We could do other things if we had other things to do, but we don't have anything to do. So just continually call libesoup tasks. And whenever it receives a message, a response to this message, it will call our callback function. And our callback function could do some intelligent processing given the status of the coil we've just read back. But because this is just a little simple test, we're going to print out the message we got back. Now this last if part, the protocol, the Modbus protocol, there's a number of different function codes which are defined. There are huge gaps where you can define your own. So there are standard function codes, and then there are function codes you can make up your own function. If the code isn't used by the standard, you can make up a proprietary message. But if the top bit is set, that indicates an error message from the slave. So that's why we test here, is the top bit set on the function code we've returned back from. So if we sent to the slave a function code of 2, which is read discrete inputs, then our slave would set that bit, the top bit, and send it back, and it would become an error code. We don't handle error read discrete inputs, so our node only processes read coils at the minute. And that's just all this master does. Every 10 seconds send a request and call this callback function when we get a response. So if I connect to its serial logging port, if it hurries up. Now we're using 19K2 for the serial login. Our Modbus channel is operating at 9600, but that's a different serial port. So carrier watch is off and connect. So now if I turn on the master, now there was obviously a spike on the line and we got a start bit, so we've got a bad message. The slave has interpreted this as a bad message. But if I turn it off now, so this is our slave. Our master has sent a request. Sorry. Now this looks a bit different from the master is supposed to send us 1 byte with a function code of 1, and then 2 bytes for the starting address and 2 bytes for the number of coils. But what we've got is that's actually in this message. This is the application layer message. So those are the 5 bytes. When that frame is sent down to the layer 2, which is the data link layer, adds on our target address. And layer 2 also adds on a CRC on the end. So the master sends those bytes to address 1 down to layer 2. Layer 2 prepends the target address, sorry, I missed 1 byte. Our application, master application, sends down those 5 bytes. The layer 2 protocol prepends our target address, which is 1, and a CRC. 2 bytes of a CRC to error check that message. Now when the slave reads this message, it's going to check the CRC and strip it off if it's valid. If it's received a good message, then it's fine. It then is going to check the target address, and if this is not for my node, it's just going to ignore it. So our API callback will never be called. So if this is for another node, just ignore it. If it is for this node, then it actually sends it on up to, it sends it up to our slave callback. And the slave callback processes all messages, all function codes. So this message, this callback never deals with addresses. So if this callback receives a message, a layer 7 message, it was from the master for this address. And now we just check our function code. The first byte, is it a function code we handle? MODBUS read. And if so, we strip off the first byte and reduce 1 from the length. And that means that this is what the message which will get passed to our callback. Because it's function code 1, we will send the 4 bytes which are significant onto the function which processes the read coils request. So you can see it prints out the bytes that it received, and there should only be 4. If there's not 4, there's an error. Send an error response. And if it's not for coil address 0, send an error response as well. And we're sending back 1 byte. So our response is, if everything checks out, it's for this node. It's a read coils request for address 0, which we handle. Then we send a response 1 byte, and the 1 byte we send back is the value 1. So the coil is on. And that goes back. So that's what we process in the slave. Coil address 0, number of coils 1, and the master gets a callback to say it's received this frame, and it's 4 1s because the request is coming from MODBUS address 1, that's slave 1. The function code is 1, this is a response to the read coils message. This is the number of bytes we're going to get back. We're only getting 1 byte, and this is the actual byte of data. The coil is on, and that's MODBUS. It's a very simple protocol. The 2 documents for layer 7 and layers 1 and 2, well, to be fair, this lower layer 1 and 2 document specification just basically says the physical layer is either RS-232 or RS-485. So that document then just specifies the layer 2 data link layer type implementation, where it goes into both the addressing and the CRC is specified in there, which is the error checking on the frame. Is all done on that layer 2 protocol. But both those documents are, the 2 combined are probably less than 100 pages, so it's probably one of the smallest, shortest protocols you're ever going to read. And this is just an implementation of that protocol. Now, the code is on GitHub. Now, this is a really bad this is potentially a really bad implementation because I've implemented this. I may have misread the standard, the specification for the protocol, and because I've implemented my misunderstandings in both the master and the slave, this works. So we can see this communication between the two. We're getting the message we expect on the slave, and we're getting the response we expect on the master. But this may contain misunderstandings when I read the protocol. Now the implementation is not fully compliant or anything. There's only the RTE mode, and T15 I haven't implemented. There's no processing of responses from the wrong slave. Stuff like that I haven't implemented. This is just a bare bones implementation of RS485. So the next step would be, having implemented this, is to take our master, and instead of connecting it to another cinnamonBun, talking to an implementation that we've written, we would take it and connect it to somebody else's RS485 device and have it talk to that, and make sure that we could talk to a device that actually implemented the standard. And conversely, we would go to and find a master device and have our slave implementation talk to it, and just check that those two combinations work, and then we're happier with. Now I'm sure if you go to MODBUS homepage, there is probably some process you can go through to get your device certified as being compliant with the standard. Usually there's various events that I won't get into that, but yeah, there should be some mechanism whereby you can get your device certified. This is just an example of the protocol, and I hope it's useful. It's an introduction to MODBUS, it's an introduction to the OSI 7-layer model, and it's actually doing something more constructive perhaps with the communications, rather than just sending text messages and test messages back and forth over RS232 and RS485. Thanks a million for watching. I hope that's useful to somebody. The code is on GitHub. Those two projects are there. You can look at the code. If you've got a device, you can build them, test them, see how they work. Again, thanks a million for watching.